welcome to our next video where we're looking at the normal and Cartesian equations of a plane. This is a different way of thinking of a plane. It's not about two directions parallel to a plane. It's about one direction which is perpendicular to the plane. You may remember I asked you to place a pen on your desk perpendicular to the desk, and notice that that direction is perpendicular to any line that you happen to draw on your desk. That's the idea behind this representation. So we're given a normal vector ABC perpendicular to the plane, and what we also need is a fixed point on the plane in order to uniquely determine the plane. Think about it. You could have a normal vector shown by a pen perpendicular to your desk, but if you put a book on top of your desk flat, then the normal vector is still perpendicular to that surface, and to put another book on top of that, and so on. So to fix the actual plane you want, we need a fixed point. And then, as always, we want an equation which is satisfied by R, a general point on the plane. But what we can certainly say is that if A is a fixed point on the plane and R is allowed to be any point, then the vector AR has to be perpendicular to the normal. And of course we know that means the scalar product with the normal is 0. And then filling in the boxes, what is n? It's ABC. And what is the vector AR? It's the position vector of R minus the position vector of A, which is that. And then it's very simple to multiply this out with the scalar product to get this relationship. And then when we rearrange that so that we have the general point on one side, x, y, z, and everything else on the other, we get this. Notice that ax1 plus by1 plus cz1 are going to be fixed because we're given them. And that's the Cartesian form of the plane given here in the formula book, where they've written D for the result of this. And notice, like the end of the last video, the coefficients of x, y, and z give the components of the normal vector. Okay. So if we see an example here, example 39, find the equation of the plane pi, which contains the point a minus 1, 1, 2, and is normal to the vector 2i minus j minus k. You could pause the video here for a moment and try to figure that out. It's pretty easy. Pause. And here's what you should have had. There's the Cartesian form of the plane. And then if you look at B, you may find it's a misprint. Hence show that the point B, 0, 4, minus 1 lies on the plane. If that were true, then these three coordinates should fit this equation. And actually they don't, do they? It would give minus 4 subtract minus 1, which is minus 3. So in fact, we can prove that B is not on the plane. Finally, if we go back to the previous video where we had we determined this Cartesian form of the plane using elimination, which I said was an unusual method. If we take the two directions that we found and look at the cross product, which I asked you to do in the last video, you should find they give either 1, 3, 1 or something parallel to that. So you could run through the procedure and use the vector product here to find this equation in a much quicker way than with elimination in the previous video. By now you should be ready to do this homework. I hope this helps, and let me know how it's going.